Okay, let's just dive right into this explainer by asking a super fundamental question about the physical world that literally powers our modern lives. If you're studying Class 12 physics, you probably already know that semiconductors are the absolute bedrock of the electronic age. But to truly grasp how a diode or a transistor actually works, we have to zoom way in and look closely at the materials themselves.
Right, so what actually separates the standard copper wire in your wall from the incredibly complex microchip inside your smartphone? The answer all comes down to the atomic structure of these materials. Like, why does copper let electricity just flow freely, while a piece of silicon kinda needs some convincing? Today, we are going to figure that out by starting with the fundamental rules of the universe that govern solid materials, and we'll build all the way up to the ultimate electronic team-up, the p-n junction.
So here's our totally straightforward roadmap for today. 1. Materials and energy gaps. 2. Intrinsic semiconductors. 3. Doping, adding impurities. 4. N-type versus P-type. And wrapping up with 5. The p-n junction. Let's get right to it.
Okay, Section 1, Materials and Energy Gaps. Let's start with the micro view and establish the ground rules for how electricity flows through different solids.
Basically, we classify solids based on their energy band gaps. That's the EG you're seeing here. In normal conductors, like copper or silver, the valence and conduction bands actually overlap, meaning the energy gap is literally zero. So free electrons are just always available, no matter the temperature. On the flip side, insulators like diamond have a massive gap. We're talking greater than 3 electron volts. Almost no thermal energy can push an electron across that canyon. But semiconductors, things like silicon and germanium, they sit right in that sweet spot in the middle, with a small gap of less than or equal to 3 electron volts. So, at normal room temperature, just enough electrons get the thermal energy they need to jump across.
And this leads us to a completely brilliant duality that is absolutely crucial to remember, especially for your exams. Listen to this. When you heat up a standard conductor, its resistance actually rises because the atoms vibrate more and scatter the electrons. But if you heat up a semiconductor, it actually lowers its resistance. No way, right? It happens because that thermal energy promotes way more charge carriers across that small energy gap. This weird opposite temperature behavior is the gold standard test to distinguish a semiconductor from a regular metal.
Moving on to Section 2, Intrinsic Semiconductors Explained. Let's meet the slightly flawed heroes of our story, pure silicon and pure germanium.
When these materials are perfectly pure without a single impurity, we call them intrinsic semiconductors. Check out this crystal lattice. In an intrinsic semiconductor, every single atom perfectly shares its 4 valence electrons with its 4 nearest neighbors. They lock together in this beautiful 3D diamond-like crystal structure. It is super stable and incredibly tightly bound.
Now, because of that ultra-tight structure, at absolute zero, literally 0 Kelvin, an intrinsic semiconductor behaves exactly like an insulator. Every single electron is stuck securely in a bond. But as we just talked about, at room temperature, thermal energy shakes things up. It basically knocks a few of those electrons loose. And when an electron breaks free to become a moving conduction electron, it leaves behind this empty vacancy in the bond. We call that vacancy a hole.
Think of a hole exactly like an empty space in a completely jam-packed parking lot. As cars, or in our case, neighboring electrons, shuffle around trying to fill that empty space, the empty space itself effectively moves in the opposite direction. It's wild, but in semiconductor physics, we actually treat this empty hole as a physical particle with an effective positive charge. So you've got both the free electrons and the holes acting as moving charge carriers. It's a 2-for-1 deal.
Which brings us to a massively important point for your multiple-choice questions. In a pure intrinsic semiconductor, every single time an electron breaks free, it leaves exactly 1 hole behind. It's a 1-to-1 ratio. Therefore, the number of free electrons is perfectly equal to the number of holes, and we define this perfectly balanced number as the intrinsic carrier concentration. All right, Section 3, Doping, adding the impurities. We have a tiny problem with these pure intrinsic semiconductors. The problem is, they just aren't conductive enough at room temperature to actually be useful for building devices. Their baseline conductivity is just way too low. So, we need a scientific superserum, and that process is called doping. Doping is just the deliberate addition of a tiny amount of a specific impurity. We're talking literally just a few parts per million. By carefully sneaking in atoms that are roughly the same physical size as silicon or germanium, we don't mess up the original crystal lattice, but we skyrocket the conductivity. Once we do this, the material gets a new name. It becomes an extrinsic semiconductor.
When you look at the side-by-side comparison, the transformation is honestly night and day. We go from a pure, practically useless material with super low conductivity straight to a doped material with incredibly high conductivity. Plus, doping intentionally creates a really useful imbalance. Depending on the exact impurity we drop in, we get distinct majority and minority charge carriers, and that is what makes the material ready to be put to work in the real world.
So Section 4, N-type versus P-type. Let's break down the two specific flavors of doping we can actually use.
Flavor number 1, N-type. Remember, silicon and germanium have 4 valence electrons. If we dope the crystal with a pentavalent element, meaning it brings 5 valence electrons to the party, 4 of those bond perfectly with the surrounding silicon. But that 5th electron, it's just left hanging there as the 5th wheel. It's super weakly bound and takes basically 0 energy to become a free-roaming conduction electron. Because this impurity freely donates an extra electron, we literally call it a donor impurity.
Now, totally contrast that with p-type doping. For this flavor, we dope with a trivalent atom, one with only 3 valence electrons. It happily bonds with 3 neighboring silicon atoms, but it is straight up missing an electron for that 4th bond. And boom, that creates a permanent vacancy, a hole. Neighboring electrons can very easily jump into this hole, which just leaves new holes behind them as they move. Since this atom actively accepts an electron to fill its missing bond, it's called an acceptor impurity. To summarize, in N-type, electrons are the majority carriers. In P-type, holes rule as the majority carriers.
Let's rapidly rattle off the most common dopants, because you definitely want to lock these in your memory for test day. For N-type, we grab group V elements like phosphorus, arsenic, or antimony. For P-type, we look over at the group 3 elements, using stuff like boron, aluminum, or indium. Got it? Awesome. Now here is the absolute golden rule of doping. Even when we completely flood an N-type semiconductor with tons of extra electrons, or a P-type with extra holes, the chunk of material as a whole remains completely electrically neutral. It balances out, and mathematically, the product of the electron concentration and the hole concentration is always a constant at a given temperature. It perfectly equals the square of the intrinsic carrier concentration. Write that formula down, for sure.
Finally, Section 5, the p-n junction. This is the absolute climax of our explainer today.
We've built highly conductive N-type and P-type materials, right? Well, the real world-changing magic of modern electronics happens when we smash them together to create a boundary. Now, we don't just physically glue them together. We actually dope a single continuous crystal so one half is P-type and the other half is N-type. And let me tell you, creating this p-n junction is definitely not a peaceful static event. The exact millisecond that boundary forms, it kicks off a microscopic, high-stakes tug-of-war between 2 fundamental forces, diffusion and drift.
Let's watch this microscopic battle unfold step by step. First, you have a massive crowd of electrons on the N side and a huge crowd of holes on the P side, and they naturally want to spread out into the empty space. This concentration gradient causes a massive rush across the border. That's called diffusion. But as these mobile carriers migrate, they leave behind fixed, oppositely charged ions locked in the crystal lattice. This creates a sort of no man's land called a depletion region that is totally wiped clean of mobile charges. This literal wall of fixed ions builds up an intense internal electric field which physically shoves charges back the way they came, a counterforce called drift current. This frantic tug-of-war continues for just a moment, until diffusion perfectly matches drift, reaching a beautiful dynamic equilibrium where the net current is exactly 0.
And that frantic microscopic battle leaves us with an absolutely incredible piece of human technology, the unbiased p-n junction. Because of that depletion region and that built-in electric field, this tiny boundary fundamentally wants to allow current to flow easily in one direction, but slam the door completely shut in the other direction. This delicate equilibrium is literally the foundation of every single diode, photodiode, and transistor on planet Earth. So the provocative question I want to leave you with is this. What happens to that carefully balanced depletion region when we attach a battery to it and crank up the voltage in forward or reverse bias? Well, that is the ultimate secret to building rectifiers and logic gates, and we are going to dive deep into exactly that in our next explainer. Until then, keep questioning and keep learning.